In this video, we're getting into kind of the nuts and bolts or the details of how we describe the location of electrons within an element. So even though there's a lot of quantum weirdness and unknowns with this, we still kind of define the most probable location of electrons, and we use different formats and notations to describe that. We talk in terms of energy levels, and we break those down even into smaller pieces. So if you've done electron configurations in the past, hopefully this is a review that really clicks in and makes sense. If you haven't done them, try to pick up some key ideas through this conceptual video that then we'll be applying and using in the next few. So as we're doing this, we are still going back to the basics of the Bohr model that we're all familiar with, which is that planetary model with the rings. So first and foremost, every current model of the atom still describes electrons as existing in energy levels. For the elements that we have discovered and we're trying to describe right now, there are 7 energy levels that the elements would be using to fill or would be using with their electrons when they're in that most stable, lowest ground state electron arrangement. There's definitely more levels than 7. A lot of times they say that this number could be anywhere between 1 and infinity, but really we're going to focus on 1 through 7. When you get to college, you might see these things described as quantum numbers. There's lots of different ways that we can think of quantum numbers as possible solutions to the Schrodinger equation, as descriptions of this and that. But the energy level, or what would be called the principal energy level, is represented by the letter N. We're not going to go through all the names and details for these, but this is something that you might see later described differently with a little bit more practice and memorization required. But the energy level is just the average distance from the nucleus. So those high energy levels are far from the nucleus. The low energy levels are close, and it's related to which row we're in on the periodic table. But we have found through experimentation, through properties of elements, through photoelectron spectroscopy, that those rings or levels are actually broken into smaller sections. Those smaller sections are called sublevels, and currently we only use 4 types of those sublevels with the elements described by the periodic table. But there's definitely more than that. They're represented by letters. So energy levels are represented by numbers 1 through 7. Sublevels are represented by letters S, P, D, F, and then we continue beyond them. Level 1 is the smallest level. It's that ring closest to the nucleus. It can only hold 1 sublevel. Level 2 has 2 sublevels. Level 3 has 3 sublevels. Level 4 has 4 sublevels. Level 5 has 5, etc. Those sublevels are represented by letters S, P, D, or F. And each of those sublevels is actually broken into smaller sections or broken into things we call orbitals. So the S sublevel is just one single place that we can put some electrons. The P sublevel is a bigger sublevel. It's broken into 3 areas or 3 orbitals that can hold those. The D sublevel is even bigger. We don't get to the D sublevel until we're on level 3. So as we get bigger, not only do we have a larger ring, not only are we farther from the nucleus, but we can also break that area into more smaller sections holding a larger number of electrons. So the D sublevel has 5 orbitals. The F sublevel, once you get to level 4, is actually 7, really weirdly shaped things. These orbitals are the 3-dimensional area in space that describes the probable location of the electron 90% of the time. So there's a lot of qualifiers there, but we'll say this is just basically where that electron or electrons are zipping around. Each orbital, whether it's an S, a single one of these P, any one of these D, or an F, can only describe or hold 2 electrons. So that's what this is talking about. This S sublevel, whether it's on level 1, 2, 3, 4, 5, 6, or 7, is a single 3-dimensional area or orbital that can hold 2 electrons. The P sublevel, well, whether on level 2, 3, 4, 5, 6, or 7, are 3 regions or 3 orbitals that can hold 2 electrons each for a maximum of 6. The D sublevel is on level 3, 4, 5, 6, or 7, which can hold, has 5 orbitals holding 10 electrons. And once we get to levels 4 and 5, we start to fill the F sublevel. The F sublevel can hold 2 per orbital, but it's 7 orbitals, meaning 14 total electrons. I did describe orbitals a lot already. Those orbitals are those 3-dimensional areas in space. Any orbital, S, P, D, F, or even once we get to G, H, or I, can only hold 2 electrons, and they have different sizes and different shapes based on how close they are to the nucleus and which type of orbital they are. This video, you can click if you want a more 3-dimensional version of what it means to have orbitals in level 1 and in level 2 and in level 3 and in level 4, and how they would go one after another. In the classroom, we have 3-dimensional models that also show these things. If you have a hard time seeing what these pictures might look like in actual space, but the nice thing, that video, those models, all of them fit those things, really just imagining these as a place or a seat or a home for an electron, and not needing to know the shape, the size, any of that, is where we end. The last thing that we describe as we're thinking about, well, where can an electron be? How much energy does it have? And what is it doing? Is its spin. Electron spin describes whether they're spinning one way or another. We represent those as arrows. And the reason spin is important, or the way we discovered spin, was by recognizing that based upon these levels, sublevels, and orbitals, some elements and molecules are predicted to be magnetic, whereas others are not. That comes back to the property of electrons. So as we start to do these diagrams, we'll see some instances of this. If we have an element in which every single electron is paired with another, and up is paired with a down, that is not a magnetic atom or molecule. It is diamagnetic, or the magnetism dies, is the way we think of that. Di meaning 2. All of those electrons are paired up. It can't be magnetized. Paramagnetic things are things that are possible to be magnetized. They are attracted to a magnet. Some of them can even be permanent magnets. Iron, there's ferromagnetism beyond this, but that's where you have some unpaired electrons. The more unpaired electrons you have within your levels, but more importantly, your sublevels and your orbitals, the more magnetized it can become, or the more likely it's going to stay permanently magnetic. So this is kind of the groundwork, or the theory, or really the terminology we'll use in the next few videos. And those are where we will explain and apply what it means to find the location or describe the location of electrons within an atom.